All right. Okay, so let's get started. Technology is working today, which is great, given what happened on Friday. So if you weren't here on Friday, somebody had, I found out afterwards what happened was somebody had gone into here and yanked an adapter out. And so I'm pretty sure it wasn't, one of the instructors or whatnot, because these are key locked. I can't even get into that. And so the computer was working, but it wasn't projecting to the screen. So we didn't record the lecture. We ended up going retro and doing the problem on the blackboard. So here's what I did as a result. So first off, we weren't able to do the QR code on Friday, so I just counted everybody present. So I just said everybody was there. Even though I'm sure that wasn't the case, I just let's just go ahead and do that. First off, let's talk about homework. So everything up to 3.5 has been graded, and the TAs are currently working on 3.6 and 3.7. Now, no homework is due today. What I decided to do, given how weird lecture was on Friday, is instead of having a separate 4.1 and 4.2 assignment, between the two assignments there were going to be 3 problems. I said, let's knock one of those out and just call it 2 problems, and let's just make it due Wednesday. And so there's one simply supported structure, one structure with a fixed support, which fixed supports are what we're going to deal with today. And that'll be due on Wednesday. Okay? Now, what we'll do today is we'll continue our discussion into the land of equilibrium in 2D, and then we'll continue on into 3D. But I wanted to take a little bit of time and discuss logistics moving forward. Okay, so first off, let's talk about this Friday, which is October 14th. I'm not going to be here. I'm going to be in Mississippi meeting with a funding agency that's funding some of our research here, so obviously I won't be here. What I did this weekend is I recorded that lecture, and I have it. It's actually in my YouTube channel now. I just haven't made it visible. What I'll do is we'll come in Wednesday, we'll do lecture 22, and then I'll make 22 and 23 visible, and then we'll talk about how the logistics will feed into the upcoming exam. And again, for that day, since I'm not going to be here, I'm just going to count everybody present. So figure that's fair. So far, so good? All right, let's talk about schedule moving forward. Okay, so today is October 10th. We're in lecture 21. We don't have any homework assignments due today. Today, what we're going to be talking about is fixed boundary conditions in 2D. So between the previous lecture and this lecture, we're covering reactions in 2D. And then Wednesday and the pre-recorded lecture are going to be discussing reactions in 3D. Really, these 2 lectures are sort of covering the same thing. The only difference is we just have different examples. So really, if there was any day that we were going to pre-record, this is going to be the perfect one because we really cover the bulk of the topic in this lecture, and this lecture is just another example. The thing about 3D problems is they just tend to be a little bit long, so that's why we have 2 separate examples just to make sure we're covering it well. So on Wednesday, we have this combined homework assignment due, and then I'm assigning homework 4.3. The thing about 3D equilibrium problems is that they're just long, so I'm only giving you one assignment, homework 4.3. I'm giving it to you on Wednesday, but I'm going to make it due Monday. I'm going to give you a little bit more time on it, just because by the nature of the problem, they just happen to be longer. I can't really do anything about that, but what I can do is give you more time on it. So far, so good? So Friday's lecture is going to be pre-recorded. We're going to that'll be posted probably on Wednesday. When we come back next week, that Monday, I'm going to begin the next unit, which is looking at deriving expressions for centroids. But this is not going to be on our second celebration. And speaking of our second celebration, the following Wednesday, so 9 days from now, we're going to have our exam review, and we celebrate on Friday, October 21st. And then when we come back the following week, we just get back into regular business talking about centroids. Okay? So does everybody kind of have an understanding of the schedule? All right, any questions? All right. Given the debacle that we had with the lecture notes and whatnot during the last lecture, I thought I would take a second and sort of go through those slides really quickly. A lot of this stuff you've already seen, or I guess I should say heard from the last lecture, but I wanted to make sure that it was covered well, and especially given the fact that some of this stuff is going to be relevant for the example that we're about to do with fixed supports. So we talked about before the concept of two equivalent systems. The sum of forces in system 1 equals the sum of forces in system 2, and likewise with the moments. The two systems are equivalent if the sum of their forces and the sum of their moments are equal. But now we're in the land of 3D, or now we're in the land of equilibrium. And what equilibrium states is that a system is in equilibrium if the sum of its forces is 0 and the sum of its moments is 0. For systems that were just particles, where all the forces were all meeting at a common point, we didn't have to worry about moments. Now we do, because now we have systems where the forces don't all meet at a common point. They're all coming in all different directions. Now, in 3 dimensions, that means we have 6 equations, 6 unknowns. This is kind of what I meant when I said we're just going to have longer problems in the land of 3D. There's really no way around it. In 2 dimensions, though, the problems get to be a lot more manageable. In fact, you will find a great many engineers will do their very best to take problems and idealize them in 2 dimensions as much as possible. Do you lose a little bit of accuracy when you do that? Yes, probably. But baked into that loss of accuracy is usually a bit of conservatism. In other words, you tend to overestimate the amount of force inside the system or overestimate the system response, which is always good in terms of design. We want our designs to be conservative and safe. So yes, we do lose a little bit of accuracy when we do that, but in the land of engineering, that's actually probably okay. Now, what we talked about last time, though, was the concept of boundary conditions, and what boundary conditions are the external forces applied to a system that are intended, that are there to keep the structure in equilibrium. And so I used this example in class last time, the awning between the 2 engineering buildings, and I said, okay, if I was modeling, let's say, these columns, I would probably model the boundary condition on the floor or on the ground as a fixed support, whereas I would model the boundary condition on the top as a pin support. The difference being is that the pin support will prevent translation, but probably isn't stiff enough to prevent rotation. Okay, whereas this column here on the ground, assuming that column is embedded into the ground deep enough, that point on the ground is not only prevented from translating, but prevented from rotating it as well. And so from that, we got into the 3 main boundary conditions that we deal with in 2 dimensions. And your textbook has oodles more of them, but I want to go through the basics again. And I kind of wanted to show you some real world examples of these so you can kind of see what's going on. And forgive me, I'm a civil engineer, so a lot of my images are related to the land of civil engineering, but I think that there are mechanical observations that you can glean regardless of your discipline. All right. So, for example, the first and arguably most common is a pin support. Now, I want to focus here on this image on the top right. This might not strike you as a boundary condition or a support that we would idealize as pin, but I can tell you that in the land of engineering, we would. So I've got this column, and I've got these beams framing into the column, okay? I propose that if I were to analyze those beams, I would analyze those beams where the end condition would be pinned. And some of you would be thinking, well, wouldn't it be fixed? Wouldn't those ends be prevented from rotating? And the answer is not really, or not really enough given the magnitude of loads that these beams see. Typically, in civil engineering structures, if we want a boundary condition to be fixed, we would connect both the flanges and the web. So a little bit of terminology for you. If you have an I-beam, right, so top plate, bottom plate, middle plate, we have terminology for those. The middle plate is what we call the web, as in Spider-Man, as in the web, and then the top flange, the top part, the bottom part, we call those flanges, okay? So if you're ever seeing a steel structure being erected, maybe such as the Innovation building on 4th Avenue, or the building on the Innovation District on 4th Avenue that's being constructed, take a look at the framing. Take a look at the beams framing into it. If the flanges are not being connected, that's probably going to be idealized as either a pin or roller support. Whereas if the flanges are directly being connected, most likely it's going to be a fixed support. And so this might also be another real-world example of that. Again, a support that prevents translation but allows rotation. So that's sort of the difference there. Rollers are reactions that only resist in the direction of rolling. It really doesn't matter which way the roller is. It's going to resist perpendicular to the ground. If you remember, a very common set of boundary conditions that we talked about on Friday were pin supports and roller supports. And if we use both of those together, we have a name for that. We call that simply supported. We see that all the time in structural engineering. Again, forgive me, I'm a bridge engineer. I relate a lot of things to bridges. But a good example of pinned and roller supports that you might see in the real world are, for example, fixed and expansion bearings in bridges. So I see a lot of people here wearing hoodies and jackets. Is that because it was a little chilly out? Whereas a month ago, it wasn't so chilly, right? It was pretty warm. Okay, so a lot of the bridges that are outside undergo a fair amount of thermal gradient, right? There are hot days and there are cold days. When things heat up, they expand. When things cool down, they contract, right? Bridges are no different, okay? So we like to have some supports that are fixed and some that allow that expansion, okay? And so you can, if you ever are on a DOH inspection, take a look at the region here that connects the beams to the abutment, if you can, if it's not encased, as if it's an integral abutment or whatnot. But you'll typically see fixed and expansion bearings. The expansion bearings might have plates with slotted holes that actually allow a little bit of translation because we want the bridge to be able to move a little bit. If we restrict it, we can get a lot of thermal stress in that bridge, and that's not very good. All right. So here's some examples of fixed supports. And again, fixed supports are ones where we are directly connecting the flanges, okay? In the land of concrete design, so for example, if you're looking at, I don't know, the 3rd Avenue parking garage, you can tell which beams and columns you would treat as fixed supports because they're all cast together. Whereas pin supports, you have these precast elements that sort of sit on top of one another. But yeah, anytime that you're directly connecting the flanges, we tend to treat that as a fixed support. And the deal with fixed supports, this is going to be the start of the show today, is that fixed supports, each of them carry 3 unknown reactions. An unknown reaction in the X direction, an unknown reaction in the Y direction, and an unknown bending moment. There is an unknown bending moment inside the support that we need to deal with. Yeah, the idea is, imagine you were holding like a somewhat flexible ruler in your hand, and you took your ruler and you pressed it. Your finger would sort of have to resist that tendency for the ruler to want to twist, and that's that moment reaction that we're trying to capture when we assess equilibrium. Does that make sense? Okay. Now we did, so here are our 3 reactions, the most common ones that we deal with. We did 2 examples, we were going to do 2 examples in class yesterday. We ended up only getting to 1. We weren't able to get to this one. What I decided to do is I had a question about, am I going to put these in the notebook? And I originally said no. I said, you know what the heck? So if you open the OneNote, you will see, so this is the first example. We did this one in class yesterday, not yesterday. We did that on Friday. And these were the answers that we got at the end. I think y'all remember that. I went ahead and put that in the OneNote, okay? I also went ahead and put the second example in the OneNote. To be honest, there's not really a whole lot that we missed. It's just more stuff to look at. The only thing with this example is, so with this example, there was a crane. The crane was supporting a 2,400 kilogram load, and the crane itself weighed 1,000 kilograms. There I go again. The crane had a mass of 1,000 kilograms, and it supported a 2,400 kilogram mass. So the first thing that we needed to do is we needed to convert that to weights. But that part's really easy. What made this example maybe a little different is that the reactions are over on the side as opposed to being on the bottom. But it doesn't make the problem any different or any more difficult. We just go about it the same way. We identify our forces, identify our reactions, take care of our equations of equilibrium, and solve it out. And I go through the math. I also try and put a bunch of notes anywhere that I think the analysis requires a little bit of explanation. But I don't really think we missed a whole lot with this example, but I wanted to include it in the notebook for posterity. I will say that in this example, I assumed both of the horizontal reactions were acting to the right. And when it was all said and done, one of them ended up being negative, which just means it acts to the left. So, again, not very difficult. Any questions on this? Would you like me to go through this in a little bit more detail? I don't want to spend too much time on it because I want to spend some time on our example today. All right. So here are the, this was the lecture I was going to cover today. One thing I did want to mention is that your textbook has oodles and oodles of different support conditions that, if we wanted, we could employ. I'm not going to get very fancy or complicated in this section of the course. All I'm really worried about are roller supports, pin supports, and fixed supports. 999 out of 1,000 structural engineering models. And when I say structural engineering, I just mean structural systems. That's not just a civil concept. That's just applies in general. Any of those systems are going to employ those three fundamental boundary conditions. Only when we get into some somewhat fancier stuff are we going to employ some of the others. And if I'm being honest with those others, excuse me, if I'm being honest with some of those others, if we're getting into the land of kinematics and design of machines, well, that's another topic in and of itself anyways. Sound good? Let's get into the star of the show today. So today, I want to look at this example. Let me pull it up in the notebook here. Oh, might need to pull it up. Let me make it a little bigger. So this is going to be the star of the show today. I have here this sort of rigid frame that's subjected to a series of loads. And I have a couple of things going on. So I've got a 450 Newton load here, a 750 Newton load here. I've got this cable, okay, and this cable is applying a tension to the frame, and it is a tension of 1,300 Newtons, okay? So I know that I've got a 1,300 Newton load right there, okay? What I want to do in this problem is determine the reactions at C, okay? Now, let's be clear. Oh, I didn't put my other line here in the end. Let's be clear, in order to do that, these are the three equations of equilibrium that I'm going to need to deal with. And before I start identifying unknown reactions, the first thing I want to do is to try and handle this 1,300 Newton force. The reason why is because that 1,300 Newton force is at an angle, okay? I'm trying to sum forces in the X direction and some forces in the Y direction. This is not oriented in the X or the Y. It's not like this one, which is obviously in the Y-axis, or this one, which is obviously aligned with the X-axis. This one's at an angle, so I'm going to split it up into its X and Y components. So let's deal with that first. So we'll call this part the geometry of the wire. So what I've got going on here is I've got a wire here that is 250 millimeters this way, 600 millimeters this way. So first off, I want to find the length of the wire. What is that? Breaking out the Casio FX115 ES Plus or similar. Anybody got an answer?
650.
650. Second? Okay, good. So this is 650. Okay? Why am I worried about that? Here's why. Be a fair statement. Remember, recall that I can take a vector and separate out its magnitude and its direction with the unit vector. So here's why I'm doing this. BD, what is vector BD? Well, it's going to be would that be a fair statement? I think it would, right? So maybe what I ought to do is compute lambda BD. Which I think we already have the magnitude of the vector. That's 650. So that's now if I'm leaving this as fractions, which I know your Casios can handle, what is 250 over 650? 5 over 13. So could we say that this is 5/13 I plus, and then what's this one?
12/13.
Or negative 12. J, right? So therefore, if I want the force, let me scroll down a little bit. If I do this, see why I left it in fractional format? Bless you. Bless you. It's that time of year, isn't it? All right. So 5/13 times 1300 and negative 12/13 times negative 12 over 13 times 1300. I think that's going to be 500 I minus 1200 J, all in newtons. Is that a fair statement? Everybody okay with that? Okay, here's the reason I did that. Okay, the reason I did that is because I want to draw a free body diagram. But I want to try and eliminate those angular loads. Okay. So let's see what we got here. Let's try and draw this to scale as much as possible. Okay, so there's my frame. All right, and so what do I have going on here? I've got this load here, which is 750 newtons. And then I have a load somewhere about right here, which is 450 newtons. Let me move this down just a little bit. Okay. Now, right here, we had this angular load of, what was it, 1,300 newtons? I'm going to replace that. And instead, I'm going to write, if you want, you can use a little dotted line to say this is 1,200 newtons, and this and maybe just the dotted line is indicating that it was a diagonal load, and I split it up into its X and Y components. All right. Let's come up with some letters to make sure that we're all talking about the same points. This is A, B, and this is C. Let's come up with some dimensions. Right there. This right here is 150. All right. Now we have a support condition down here, which I'm going to talk about here in a second. But I know that this dimension here is 400. The entire height of the whole frame is 600. And I think I've got all of my known forces and dimensions laid out. But the only thing left to deal with is this, what's going on here at C. C is a fixed support, right? So how many reactions does a fixed support have? 3, right? Now, what I'm going to do is I'm going to assume some directions, okay? And let's just assume positive directions. So we'll call this CX. And typically I like to sometimes throw a little dash mark through my reactions to indicate just that it's a reaction. We'll do CY like that. And then there's a moment reaction. Now, moment reactions are rotational, right? And so there's either counterclockwise or clockwise. I'm going to assume counter. Call that MC. Okay. Now, I want to be crystal clear. There's no magic behind these assumptions. I just guessed some. If I guessed wrong, the math will tell me. I'll get a negative answer. So if I get a negative answer for CY, it just means CY is acting down. If I get a negative answer for MC, it just means it's acting clockwise. I need to guess something for when I write my expressions, but it doesn't really matter. It doesn't really matter what I guess technically. Now, as problems get easier, I guess I should say, there are going to be points when you could just look at it and say, yeah, it's acting up, and just guess up and save yourself a little hassle later. Okay. So far, so good? So now let's start applying our equations of equilibrium. So let's start off with the first one. Summing forces in the x direction. Okay? Now, whenever you write these equations, you need to pick something, some direction as positive in order to write the equation. So we'll say summing forces in the x direction equals 0. We'll say forces that are acting to the right, positive. Okay? So what do we got? All right, so the way that you handle this is you just go through each of your forces one by one. Do I need to worry about this 750 newtons right here? No, it's vertical. I'm talking about summing forces in the x direction. What about this 450? Do I need to account for that? Is it positive or negative? Negative. Let me move this over here a little bit. All right. What about this? 500 newtons. Do I need to account for that? Yes. Positive or negative? Positive. There you go. See, this part's pretty easy. All right. What about the 1200? All right. Did I forget anything? CX. CX I've got to account for. And that's acting to the right. That's positive. I don't need to account for the CY or the MC. Those aren't forces in the x direction. So the sum of those must be equal to 0. So negative 450 plus 500 is positive 50. So 50 plus CX is 0. So what does that mean CX is? Negative 50. Does not mean I need to develop significant emotional distress. All that means is that I guessed CX is acting to the right. I was wrong. CX is 50 newtons to the left. That's it. That's all that means. Yes?
In the test, do you need to distinguish if it's acting in the right or the left direction with the arrow or?
The arrow. That's a good question. So the question is, do I care about the sign or the arrow? The answer is the arrow. The sign is only reflective of your guess. But your guess or my guess or your guess or their guess doesn't matter. No matter what anybody guessed, the answer is 50 newtons to the left. So that's what I care about. I care about magnitude and direction. Okay? Just like any vector. Make sense? That's a good question. That's a good question. Now, one of the nice things about fixed supports is that it doesn't really matter what order that you solve your equations for if you only have the fixed support. Whereas with pin supports, we kind of needed to be strategic. We sum moments before we sum forces in the y direction. With fixed supports, it doesn't really matter because we only have one unknown in the x, one unknown in the y, one unknown moment. So we can just do them in order. So let's deal with some of the forces in the y direction. We will take forces upward as positive. All right. It's just like a checklist. You go through each one of them. Do I consider the 750? Positive or negative? Negative. Do I consider the 450? No. Do I consider the 500? Do I consider the 1200? Yes. Positive or negative? Do I consider the CX? CY? Positive or negative? Do I consider the MC? Did I get them all? The sum of those must be equal to 0. So, 750 and 1200. So now, CY, if I move the 1950 over to the other side, I get a positive 1950. So what does that mean? That means my guess was correct this time. CY is 1,500 newtons acting upwards. Or sorry, 1950. Boom. Pretty simple, right? Now let's sum moments. Now, with any moment expression, we need to pick a location. Where do you think would be a good place to sum moments? C. All right, I tend to sum moments where there's a lot of stuff intersecting. And so naturally for me, C is a good place. We'll take counterclockwise moments as positive. All right, I'm going to scroll down a little bit so I got a little bit more room to write. I don't want to scroll down too far. Okay. Move that over a little bit. Okay. So now what we've got to do is we have to account for every force that generates rotation at C, okay? So the whole time, our I should be fixed at C. Let's have a blue eye. How's my artwork? Is that good? It's not too creepy? Okay. It's close to Halloween. Maybe it should be a little bit. Okay. So we take each force one at a time. Okay. Let's start off with the 750 newtons. Let's just check them off. Does the 750 newtons want to rotate point C? Yes, it does. Okay. In what direction? Are we talking about counterclockwise rotation or clockwise rotation? Counterclockwise rotation. So if it's counterclockwise rotation, is that a positive moment or negative moment? Positive moment, because we're taking counterclockwise rotations to be positive. Now, what is the moment arm? What is the shortest distance from the line of action of that 750 Newton force to C? Say it again? 500, exactly right. So this is going to be positive 750 newtons times 500 millimeters. That's exactly right. What about 50? Is it causing rotation? All right, is that counterclockwise rotation or clockwise rotation? It's counterclockwise, which makes it positive or negative? Positive. And the moment arm, how far is it from the line of action of this force to point C? 400 millimeters. So positive. Boom. Tell you what, this is gonna get long. Can't do that on a whiteboard. Okay. What about the 500? Does it generate rotation at C? Counterclockwise or clockwise rotation? Clockwise rotation, so that's negative. So negative 500 newtons times what? What is the moment arm from that force to point C? Now, hold on. Okay. So all right, this is great. This is a great point. Okay. So we're talking about the 500 newtons. We're talking about the line of action of that force to point C. What is the shortest distance from that line of action to point C? 600, right? All right. Now, what about the 1200 newtons? Does it cause rotation at C? Yes. clockwise rotation or counterclockwise rotation, which makes it negative. So negative now, what is its moment arm? How far is it from the line of action of this force to point C? 150. Oh, millimeters. Now let's make sure everybody's awake. Does CX cause rotation at C? No. Why?
On the axis.
Which it's going right through point C. That's basically exactly right. What about CY? No, it's going right through. Now MC causes rotation at C because that's what it is. It is a rotational action. It is a moment at C. Which way do I have MC drawn? Counterclockwise, which makes it positive, right? Is everybody with me on that? So MC is going this way. That's positive, so I just say plus MC. Equals 0. Equation got longer, but not harder. Now we got to do a little bit of arithmetic. So 750 times 500, that's 375,000. And it's Newton millimeters plus, okay, 450 times 400, that ends up being 180,000. Newton millimeters. 5 times, well, that's not an equals, it's minus. 5 times 6 is 30, so 500 times 600, that's minus 300,000. Minus 1,200 times 150, 12 times 15 is 180, so 180,000. Plus MC is 0. So I got a 180, they're going to cancel. 375 minus 300 is 75,000. So therefore, MC is negative, which equals negative 75,000. And it's going the other way. It's going clockwise. So to summarize our answer, the only way that this system is in static equilibrium is if Cx is 50 newtons to the left, Cy is 1950 newtons upwards, and MC is 70. Oh, I put a negative there. I don't need to put the negative there because I already took care of the sign. Is 75,000 Newton millimeters this way, or if I'm wanting to abridge that a little bit, there's 1,000 millimeters in a meter, so I could say 75 Newton meters. That way. Either way works. We'll stop for a sec. See if anybody has any questions. Hopefully it's not. Hopefully it's pretty straightforward. Make an assumption about your unknowns. Write your equations of equilibrium, solve. You get positive answers, your assumptions were correct. You get negative answers, just flip the direction. That's it. It's that simple. Now I will tell you, 3 dimensions is no different. No different at all. The only thing is that it's longer. Longer, and I guess we don't have the luxury of just doing FD for all of our moments. We have to do R cross F. So the problems just get longer because we're having to describe vectors and then cross products and all that, but it doesn't make it any more or less difficult. Sound good? I'm going to give you 4 minutes of your life back. I'm going to pull the QR code again, but I'm going to stop the recording. That's all I got. I'll see you all on Wednesday.